So now we're going to talk about something called graph isomorphism. Fundamentally, this is about whether two graphs are the same, or whether two representations of a graph are really the same graph. And the reason I say representation is we've been thinking a lot about graphs using their drawings, right? We keep drawing the complete graph on 4 vertices like this, right? As sort of the cycle with 2 diagonals. But there are other ways we could draw it, and there are sometimes we might want to. For example, we could draw it like this, if maybe we didn't want the edges to cross, right? And we can convince ourselves without too much trouble that this is the same graph, right? It still has 4 vertices, and they all have edges to every other vertex. So it must still be K4. And if you want to sort of see it morph into this other version, think about dragging this center vertex out this way. And then sort of stretching those edges, and eventually it'll look like that. So in this fairly small example, right, we can sort of look at it and identify that these two must be the same. But it's helpful to be able to do this in general. To do that, we need a good definition of sameness, though. In particular, we need to define an equivalence relation. So there's a jargony way to do this and sort of an informal way to do this. We'll talk about the more jargony way in class, right? The formal, what we actually need. But the idea is, if we have 2 graphs, G and H, we want a function that goes from the vertices of G to the vertices of H that keeps the edges the same. Right, so let's say that U and V are vertices in G. And there's an edge between them, right? UV is an edge in G. Right, let's call our function f. I'll name it there. So now f of u and f of v are vertices in H, right? Let's give them names. Let's say f of u equals A and f of v equals b, right? AB has to be an edge in H. And we need the opposite to be true as well, right? If AB is an edge in H, then we need UV to be an edge in G. So formally, right, the formal language is that we need this function to be a bijection, right? We'll talk about an edge preserving bijection. Okay, this is all sort of abstract though, so let's make a drawing, some examples. So here's the example I had in class. Okay, so this graph is G, and here is H. And looking at these, we can, sorry, let me try that again. Here we go. We can convince ourselves that these are the same graph, right? We're sort of switching this path and this path in G to become this path and this path in H. But the way we would actually prove it is to come up with a function from the vertices in G to the vertices in H that keeps all the edges the same, and vice versa. So here's one way we could do this, right? I could label all of the vertices in G with numbers, write down what the edges of G are, and then try to label the vertices of H in the same way, such that if I wrote down all its edges, I would get exactly the same ones. So let's do this for G, right? I'll call these 1, 2, 3, 4, 5, 6. So what are the edges here? We have an edge from 1 to 2, from 2 to 3, from 3 to 4, from 1 to 4, from 1 to 5, between 5 and 6, and between 3 and 6. Okay, 7 edges. So here's a good thing to check right away. Here we have 6 vertices and 7 edges, and here we can count. We also have 6 vertices and 7 edges. That was how I knew I had messed up in my first drawing. I had the wrong number of vertices. Okay, so we want to sort of match up these vertices to vertices here as best we can. So one thing that's helpful is looking at degree. So here, the vertex that we've labeled 1 has degree 3. So if this is going to work, we need to label as 1 a vertex here with degree 3. Well, there are 2 options, this one and this one. So in this case, it will turn out not to matter which one we choose. We could look for sort of other signs in other graphs, but here it will genuinely not matter, so we just make a choice. And we can always choose and see if it breaks and then try the other way. Right, so I'll call that one 1. Well, there's only one other vertex of degree 3 in G. So if this is going to work, this vertex up here must have the same label as that one. So we have 1 and 3. And then this sure looks like 2. And now we're left with 4, 5, and 6. Well, 4 is connected to 1 and 3, which this vertex is, so let's call that 4. And 5 is adjacent to 1. So let's do this as 5, and then this is 6. Right, so this looks like it worked, but let's make the list of edges to be sure. Right, so 1 and 2 have an edge. 2 and 3. There's 3 and 4. Here's 1 and 4. The top is 1 and 5, and 5 and 6, and then finally 6 and 3. Right? So these are the same set of edges, so these two must be isomorphic. We found a function that worked and proved that they are the same. So in general, if we're trying to prove that 2 graphs are isomorphic, we need to find a function of this kind. But what about if we're trying to prove that 2 graphs aren't isomorphic? Well, there are a few things we can look for. Right? Not isomorphic? Right, we've already mentioned that if they have a different number of vertices or edges, then they are definitely not the same graph, right? They're definitely not isomorphic. But we can look at some other properties or quantities as well. Right? We could look at the maximum or minimum degree of vertices. Right? We could look at the largest paths or cycles that are subgraphs. Going back to degree, we could look at sort of degrees of vertices adjacent to each other. What do I mean by that? So if in one graph, right, I have some big graph here, right, I have a vertex here that has degree 3 and a vertex here with degree 3. But over here, you know, I have 2 degree 3 vertices, but no degree 3 vertex adjacent to them. Right? Let's say that here I just have something of degree 2. Right? I definitely can't map these two over here, right? Because my 2 degree 3 vertices are supposed to be adjacent to each other, and here they aren't. So there are a lot more things like that you can look for, but so you're thinking about sort of what characterizes this graph, and are the same things true of this graph. Another thing we could look for is, you know, if one is bipartite and the other one isn't, then they're definitely not isomorphic. Right? There are many, many ways to be isomorphic. There's really only, there are many, many ways to not be isomorphic, but there's really only one way to be isomorphic. But this is a tricky problem. Computationally, it's pretty hard to do. We'll talk more about that on Monday.